Hello, everyone. It is my honor to present our recent work today. My name is Shulu Chen, come from George Washington University. Today, my topic is competitive pricing in airline revenue management with multi-agent reinforcement learning. We have two co-authors, Dr. Saeed Shihab from Kent State University and Dr. Peng Wei from George Washington University. Our work focuses on the pricing process in airline industrials. Imagine one passenger wants to fly from Chicago to New York City, and when he starts to looking for tickets, he may find different process for different airline companies, and usually he would like to choose the lowest one. But how do these airline companies make the prices? They need to consider the live tickets, the expected passengers that may arrive, and date before departure, and even their competitors' price. The related work, Dr. Whitman in 2019 introduced the dynamic pricing mechanism for the airline industrial. Amadeus in 2017 and Dr. Shihab and Wei in 2021 used deep reinforcement learning for seat inventory control. And our contribution for this project is, firstly, we designed the multi-agent airline revenue management model. We call it MARM. And we formulate the behavior of airline companies and passengers. And it is the first work of applying multi-agent reinforcement learning to airline revenue management with computation. Now let's have a look about our problem description and some assumptions. Firstly, we focused on the single flight leg, and two agents would compete with. Now let's have a look about the problem description and the assumptions. Firstly, we focused on the single flight leg. There will be two agents to compete with each other. There will be two different fare classes, the low and high fare classes, which share the same cabin seat inventory. And at each single day, each agent offers one price for low fare class and one price for high fare class. In addition, passengers are categorized into two corresponding classes. They could not buy the tickets not belongs to its category, and passengers would always choose the lower price and have a 50% probability to choose either flight when given the same price. And when one agent sells all of its tickets, the other may monopolize the market, so it could increase its price if necessary. Now let's have a look about the problem formulation. Here we divided our problem formulation to two sides. One is for airline companies and one is for passengers' behavior. For airline companies, we use a multi-agent deep deterministic policy gradient method. And for the time step, it is each single day during the booking horizon. And for the environment setting, the state contains four factors: book tickets for high class, the book tickets for low class, the remaining seats, and the time. The action is the price for each fare class. The reward is the revenue earned at time t. For the passengers' behavior, firstly, we generate the passengers by beta distribution, and every passenger may buy a ticket depending on the willingness to pay, which is a probability related to the price and the date before departure. Now let's have a look about our MARM model. Here is the whole process. Firstly, we generate the passengers by beta distribution. For example, at day 50, there are 4 low passengers and 1 high-class passenger. And the two agents would give 2 prices at this day for each fare class. Passengers then observe and decide. Firstly, choose the lower one, and then buy or not, depending on the willingness to pay. And finally, we will compute the rewards for each agent and the live tickets. Based on the MARM model, we did 4 experiments. First tool is about the single learning agents using DDPG to update the policy versus predefined model or the pricing matching model. Then the last two are about multi-agent learning agent. We firstly did an experiment without willingness to pay, and then did an experiment to compare the cooperative case and the competitive case. Now let's have a look about the experiment 1, learning agent versus the predefined policy agent. Now let's have a look about the experiment 1, learning agent versus predefined policy agent. And in this experiment, one learning agent will use a deep deterministic policy gradient algorithm, and the other would maintain the predefined pricing policy. For the problem setting, there will be 20 days during a whole booking horizon, and there will be 40 seats per flight. The low fare class passengers would be 40, and the high fare class passengers would be 20, which means that the total seats is greater than the total passengers, which would lead to a fierce competition. And for the action space, for each fare class, there will be 8 price points to be chosen. Here is the result of experiment 1. The left figure shows the learning curve. The reward raise up with episode and then converge to a very good policy. The right figure shows the final pricing policy they obtained. The orange line is our predefined agent, which uses a fixed pricing policy, and the blue line is our learning agent, which takes a policy where the price is just slightly lower than the fixed one. This strategy enables the learning agent not only sold all of its tickets, but also gained a very good revenue. Now let's have a look about the experiment 2, learning agent versus the pricing matching agent. Here, still one learning agent using the. Now let's have a look about the experiment 2, learning agent versus price matching agent. Here, there will be one learning agent use DDPG algorithm, and the other agent observes and chooses the same price as the learning one. Other settings are totally the same as the experiment 1. Now let's have a look about the results. We can see from the left figure that the reward raise up but lower than the previous experiment. It is because the other agent shares the market with him. And the right figure shows that the price raises up with time, and it makes sense in real life because passengers would have higher willingness to afford a higher price when it is near departure. Now let's have a look about experiment 3. 2 learning agents compete without willingness to pay. Here, we will have both agents to update itself by using the multi-agent DDPG algorithm, but we eliminate the willingness to pay to reduce uncertainty, and other settings are totally the same. The result of these experiments are very interesting. We observed 2 different scenarios during training. The first scenario is in the red box, and here is the result of these experiments. The result of this experiment is very interesting. We observed 2 different scenarios during training. The first scenario in the red box shows that one agent achieves much better revenue than the other, and the total revenue is suboptimal. The other scenario in the green box shows that the agents have the same policy, and each agent achieves lower revenue than the previous one, but their total revenue is optimal. And this leads to a question. So which situation should we expect it? Better total reward or the better single reward? Based on that question, we did the experiment 4, cooperative or competitive. Here, we added willingness to pay back and compare two different cases. If the target of the both agents is to increase their total reward, we call it cooperative case. And if they only aims on their own reward, we call it the competitive case. And if we look inside of the competitive case, the agent would face the prisoner's dilemma every day. As the table shows, if both agents choose a lower price, they will obtain half of the low price as revenue. And if both of them choose a high price, they will obtain half of the high as revenue. But if one agent is high and another is low, the lower price agent would always obtain all of the profits, and the higher price agent would get nothing. And as a description of the prisoner's dilemma, if the game is played exactly n times and both agents no stand, the only possible Nash equilibrium is to always defect, which is always choose a lower price. And this case always happens when the supply is more than the demand. And the result of these experiments confirms our analysis. In competitive case, when agent aims to increase its own profits and there are not sufficient passengers, they would finally choose the worst case, just the lowest price at the time, all the time. The result confirms our analysis. In competitive case, when agent aims to increase its own profits and there are not sufficient passengers, they would finally choose the worst case. The result confirms our analysis. In competitive case, when agent aims to increase its own profits and there are not sufficient passengers, they would finally choose the worst policy, just the lowest price all the time. But in the cooperative case, if agents aims to increase their total reward, the final policy is much better than before, even if the passengers are not sufficient. And finally, let's talk about the challenges and challenges. And finally, let's talk about the challenges and our future work. First is about the learning instability. Because our model has too much uncertainty, just like the willingness to pay and the passengers distribution, it is very hard to train. And another main issue comes from the dynamic of the competitor's action. It would affect the environment to make the other one to Finally, let's talk about the challenges and our future work. First is about the learning instability. During training, we found that this problem is very hard to converge, and we think it comes from two things. The first is that it contains too much uncertainty, just like the willingness to pay and the passengers distribution. The other factor is the dynamic of the competitor's action. It makes the environment not stationary, so the agents are very hard to learn something from this kind of environment. And another issue is about the game theory. So which case is more realistic, the competitive or cooperative? And we need to investigate the game mechanism to design a better agent. Finally, in real life, airline companies could not absorb all of the information of their competitors. So they need to have the ability to predict its predictors. Finally, let's talk about the challenges and the future work. Finally, let's talk about the challenges and the future work. First is about the learning instability. There will be too much uncertainties in our model, just like the willingness to pay and passengers distribution, and the dynamic of the competitors' action also leaves the environment non-stationary, which means that it is very hard for the agents to learn anything. And another issue is about the game theory. So which case is more realistic, the cooperative one or the competitive one. And then we need to investigate a game mechanism to design a better agent. Finally, in real life, the airlines companies could not observe all of the information of their competitors, so they need to have the ability to predict its competitors' action. We call it the partial observation. It is one thing we need to do in the future. So here, it is all of my presentation. And here is all of my presentation. Thanks you. And here is my presentation. Thanks for your attention and hope for your comments and questions. Thank you again.